answers. And like I said, if you don't know what you're supposed to measure when you put a meter in a circuit, then don't put your meter in the circuit. Worksheets. Worksheet 1, rectifier circuits. And then, so let me make sure I can pull these circuits off here. Yes, I can. So what I'm going to do is I'm going to open up PowerPoint. And then we'll clip some in here so we can record it. So which one y'all want to work? What? All of it. Jeez, guys. So we'll look at the first one. This is and you're going to have to know the name of these circuits. So this is what we call a full wave center tap.
You asked for the name on the desk.
No, I want the name. That's the book brick. Yeah, I want the name. Knowing your abbreviations, that would be like me saying, what's your name? And you say CRR. But you doesn't have to call me Johnson. Some of y'all that's been around for a while catch that. So what's the first thing we need to do? Y'all help me out.
First thing I did,
That's good. That's good. We're okay. So first thing I got to figure out what we get on the secondary side. So the name of this is a what? Yeah, center tap. It's supposed to be in. First thing we do is you can do it one of two ways, but we'll work it that way first. So I can come up here and I can say 120 divided by 10. And so what's that going to give us on the secondary? Okay, it's going to give us 12 volts. Okay. Then what I'm going to do is I'm going to come over here and I'm going to take the 12 and I'm going to divide it by 2 because it's center tap. So that's going to give me 6 volts between here and here. Now you could have worked this different. You could have went ahead and converted it to RMS, to peak, and then divided it by 2. But you got to divide this voltage by 2 somewhere because we're only using 1/2 of the transformer at a time. Which makes it neat because the transformer is constantly swapping, so no coil is carrying full current at the same time. So that means, we can get a 1 amp transformer and basically get 2 amps of current out of it. Our diodes could be rated at 1 amp and we could be getting 2 amps of current because the currents are going to average out, right? Y'all understand what we're saying? Because they're on and off. Now what I'm going to do is I'm going to convert this to VP. We call it VP secondary. This is going to be equal to what? 6 divided by 1707. What do we got? What's that? Okay, 8.49. Or 8.5 would be good enough, guys. But if you want to carry it out that way, it's fine. In this class, we probably need to carry it out. Once we got it into correct engineer notation, we want to carry it just to 1 decimal point, unless we prove Ohm's law wrong. So what do we got? 8.5. Okay. But 8.49 is fine. If you want to carry it out that far, that's fine. Then what do I need to do? Then we need to go what we call V peak out. So this is going to be 8.5 minus 0.7. And this is critical because this is going to be almost a volt difference in our calculations. What's that?
7.8.
So this is equal to 7.8 volts. Still on the AC side, but this should be peak now. I should be putting a peak out there. So on AC voltages, if we don't put what it is, it's RMS. because we only go through one diode at a time. So if I follow this, now the full wave bridge, we go through 2 diodes. Every time we conduct current, we go through 2 diodes. But here what we're doing, when this guy here is on, this guy right here is off. So the current comes up here. It does not go through that other diode. It goes through that diode right there. And that's 0.7 volts. Okay. Now the next alternation, what's going to happen is this guy right here is going to turn on, and this guy right here is going to do what? Turn off. Now the current flow still the same direction through our resistor, but now it's going to go through that. So each direction, it only goes through 1 diode. So we subtract, and this is a problem we have is people see 2 diodes, and they don't figure out the current flow. They say that's 2 diodes, that's 0.7 volt per diode, but they don't understand it's what? One of them's on and one of them's off. So we only go through 1 diode. Did that answer your question, Jackson? You okay? Okay, so everybody with me so far? Okay. Well, wait, hold on. Okay, so what do we do next? Now we calculate our DC or our DC average. Since it's full wave, then we're going to take 2. We have 2 times 7.8, and then we're going to divide that by 3.14. You can enter in the calculator just like that. Huh? 4.9 volts, around 5 volts. The pulse frequency is going to be 120 hertz. Now, while we're doing that, that's going to come later on. So right now, we know we're supposed to get this. So if I come up here and get this, then I know one of the diodes is open. When we put a filter, it's never going to go to ground. So we're going to have to figure out another method, if I've got an oscilloscope, how I can figure out if one of my diodes are open. And the only way we're going to do that is if we know the frequency, the frequency of the pulses. Everybody understand the 120 hertz? Because my AC, for every 1 cycle of my AC, I get 2 cycles of pulsating DC. 4.9. Everybody okay? Everybody okay? I heard it so. Hold on a second. Okay, I could have done this. So there's 2 ways you can come up. As long as you come up with the same thing every time, you're okay. So some people work it like this. So what I would do is, first of all, I would calculate the full voltage of the secondary. So I'd come over here and I could say V peak out is equal to 12 divided by 0.707. And what does that equal to? What's that? What does that equal to? Okay, 16.97. Okay. And then I can take this and divide it by 2 and come up and get 8.5. So way some people see it, and it makes no difference, is some people calculate this and then divide that by 2, and some people calculate the RMS and divide it by 2. So where did that come from? Well, it come from that solving it that way right there.
Will it affect your whole compared to lot if you do that?
No, it would not affect you at all. In fact, that's what I would prefer. Okay, you'll understand that. Because you have to understand, basically, one, we're building with approximations. So if I came down here and I got 3.6 votes, that would be wrong, because that means you didn't even round right? You understand that. But if you come up and got 5.1, 3, anything, 4.6, then that would be counted right. And of course, I understand that we round. So what are we going to do in this class? Well, we're going to round to 1 decimal point. And you're exactly right. If I round that to 1 decimal point, that would be equal to 17 votes. But you notice when you calculated it all the way out, if you use 17 votes, it's still going to come up to be maybe 5 votes instead of 4.9. But, that's 100 millivolts difference, and the answer is no big deal. And that's what I look at when I calculate. But if you don't round anything, if you round everything to whole numbers, so if you come down here and you use 9 right here and you use those like that, right, you understand that could cause us a problem. Yeah, but this right here would round, no doubt, to 17. Any more questions? What do you mean?
Like how you did it right here.
Yeah, but you got to understand, I'm looking for that right there.
Okay.
And the only reason I ever will go into your equations is if you have wrong answers. Okay, y'all understand that? So how you came up with this, and like I said, some people solve it this way, some of them solve it by what we started off with, by taking the 12 votes and divide it by 2 and then solve it that way. Whichever way you see it, you need to figure out which way you want to do it. And then do it the same way every time. So don't do it one way one time and one way the other time. Okay, does that make sense? Yeah, that's what I'm saying. It's just like, I like to use 2v pick over pi for full wave. That's what I like to use. It just sticks in my head. But if you want to come up here and try to memorize 0.327, in fact, that's on the formula sheet. That's you get the same answer. So whichever one you want to work, do it that way. But in my mind, I know 2v peak over pi for full wave and v peak over pi for half wave, and that's stuck in my memory for years. It's just like when I learned the color code in military. I know that I don't use that one anymore because that was, and I was in the Navy, so it wasn't clean as what we teach here. But of course, I don't use it anymore, because it's in my head, right? You understand that? So whichever way you do, if this is the way you prefer, that's fine. And like I said, these formulas are on a formula sheet, and you're going to be able to use that formula sheet because there's a lot of formulas in this class. And why we do this is you may or may not ever use these formulas again. But if you understand the math, then you understand the circuits, right? You understand. And now the circuits make sense. But on every one of mine, now I think what else did we ask you to solve for? Did we ask you to solve for I? So I of the load would be equal to 4.9 or 5 volts divided by 2.2K. So what do we get there? 2.2 milliamps. Anything else I asked you to solve for? Should solve for power too. So here we can say power is equal to V times I, which would be 4.9 or 5 times 2.2 milli. What do we get? So if you just write down 11, that's the wrong answer. 11.2 milliwatt, that's fine. Milliwatts though, right? So we could use a real small resistor in this circuit. So anytime you start dealing with R, then you better solve for the power, because what you're going to find out that electronic devices are rated in 2 different things, at least 2, some of them are 3. And what's the two things that resistors are rated in? Yeah, wattage and ohms. Actually, it's three. Wattage, ohms, and what? And then a tolerance. So just because you know ohms don't mean very much. Because if you put the wrong wattage resistor in there, either you're going to be paying more money than you need to pay for it, or you're going to burn your resistor up. One of two things. I think I told you about the power supplies, right? About them just picking out a 100 ohm resistor. We had like a 15 volt power supply. And they were going to use 100 ohm resist. They was going to use a 100 ohm resistor. So 15 volts, that would be V squared over R. That would be the power. And what resistor was they using? They was using a 100 ohm resistor. And they were using quarter watt resistors, and they were burning them up as fast as they put them in there. And they thought it was something wrong with their power supply. Something's wrong with my power supply. It keeps burning up resistors. Well, all they knew is they wanted a 100 ohm resistor. They went and did what? They just grabbed a 100 ohm resistor. That'd be like putting a lawnmower tire on your car and trying to inflate it to 40 pounds. So what does that come up to be? V squared over R? 15 volts squared divided by 100. I don't have my calculator, but I'll do that. Yeah. Yeah. Okay, guys, you okay? So anytime you ask for a resistor, one thing when you need a resistor for your kit, you say, Rich, don't come up and say, you'll say, I need a 100 ohm resistor. You know my next response is going to be?
What's the color?
What's the color code and what's the power rating? Okay. So I guess we'll work number 2. So what type of circuit is number 2? We solved for everything we needed to solve for? Okay, this is a halfway. This is a negative supply. How do I know it's a negative supply? Cathode's pointing toward the source. Good job, guys. That's a good answer. So my voltage answer, you don't have to use signs within the math. It don't make any sense. There's no such thing as a negative current. Y'all understand that? There's no such thing as a negative current. We have a negative voltage. There's no such thing as a sign. AC has no sign. So the only time you really need the negative sign is when you do what? When you put your output, what the output voltage will equal. So this is a lot easier. So what's the first thing I need to do? We could, so we could do two things. I could come over and I could take 120 volts. I could calculate my V peak on my primary. You'll notice, so I could take 120 and I can divide that by 0.707. And what does that give me? Yeah. 169.7. Right to understand. Then I could calculate V peak on the secondary, and I could take 169.7 and divide that by 5. What would that give me? Okay, 33.9. Okay, so that's one, right? Or I could do what? I could have calculated VRMS on the secondary. I could have said 120 divided by 5. What does that give me? 24. Then I could calculate the peak secondary, and then I could have said 24 divided by 0.707, and got what? Well, that's what I'm saying. So you could either go ahead and take the peak, you could go ahead and convert it to peak before you go through the division ratio, or you can divide RMS and then convert it to V peak, and you get the same answer, whichever one you prefer, right? You understand? Still no signs out here. This is still AC, so there's no such thing as negative AC and positive AC. AC has no sign. So literally, people gets tied up on that black lead on their meter. They think in an AC circuit that black lead has to be connected to common. That's false. Y'all understand that? So in an AC circuit, the colors of your lead mean nothing. But you need to get used to putting the black lead in the common and the red lead in what you're trying to measure, because if you start swapping that around, it could give you problems later on. But in AC, when you make your measurements, the color of your lead makes no difference. So you could use red on common, and then you can use black to measure in the circuit. You can swap those around, and you get exactly the same thing. So now we calculate what? We calculate V peak out. So I'm going to take 33.9 minus 0.7. 33.2 volts peak. Still no sign, right? Then I could come over here and calculate my DC. Would be equal to 33.2 over 3.14. So here we don't multiply it by 2 because this is halfway. And what do we got? What's that? 10.58. 10.6 volts. Now guys, this should have the what? The negative sign. This is where the negative sign should be. So DC, if you put your red lead on your common and your black lead, it's not going to hurt the meter. It just gives you the wrong sign in your answer, right? So here would be a situation where you want to make sure that you put your black lead on your common and your red lead to make your measurement, if you want the right polarity. If you're just looking for voltage, I mean, I'll do that all the time. So I'm going to come over here and measure a bunch of resistors. So what I'll do is I'll start off with my black lead right there and my red lead right there, and then I leave my black lead right there and move my red lead. Now my sign's different, and that way I can do it without constantly moving on my meter leads, right? So you'll see me do that all the time, but I understand my meter and I understand what I'm looking at actually has the opposite sign. You need me?
I'm going to send you to your office. Top 2 pages, can you sign on and change?
I sure can. So what do I need now? Need to calculate current, right? So I, the load, would be equal to 10.6 divided by 1K. So that should be around, what, 10.6 milliamps? 1K is really nice. 1K is 1 milliamp per volt. Are we okay so far? Okay. Then I need to calculate power in the load. So here we can use V times I. So this is 10.6 times 10.6 milli. So all we got. What's that? So we could use quarter watt. We could use an eighth of a watt. An eighth of a watt is 125. Normally, though, we don't get that close. We usually try to double the wattage rating of a resistor. So that means we would use quarter watt. How do you identify the wattage rating of a standard resistor? How do you know the wattage rating of a standard resistor? Color-coded resistor. Huh? No, how do you know when I'm holding a resistor in my hand? Yeah, it's the physical side. So this right here is a half watt. This right here is a quarter watt. We got some more too. So you learn the physical size of the resistor. So this would be 500 milliwatts. This would be 225 milliwatts. We got some 8 watt in there too. I can show y'all, but it's the physical size of the resistor. Now, when you get into big resistors, the wattage rating, where they have enough room to write it on it, they'll write the wattage rating on it. Now, actually, it'll be written on the resistor. Now, here the frequency of the pulses. Yeah, frequency is going to be equal to 60 hertz. So is that it? Anything else? Anything else we need to solve for? Is that everything that we asked for? Got the what? Oh, the fuse size. We'll talk about that later on. The problem is, so understand what's our current. So what's our watts? So I got 112 milliwatts right here. What would be the power in the primary? Huh? What's going to be, huh? What would be the power in the primary? What's that? The power, not the voltage. For some reason, people think about Alabama Power, and they think when we talk about power, we're talking about volts. No, we're talking about watts, right, or VA. So if I've got 112 milliwatts required by my load, what would be the power required in the primary? Guys, y'all shouldn't even be picking up a calculator. Transformers do not change power. They change voltage, but they do not change power. So that would be awful, right? You understand, I turn on my light bulb and y'all try to figure out the power transfer. So that means I need 112 milliwatts worth of power, period. All the way back to Alabama Power, or TVA, I'm sorry. My house is on Alabama Power. It's 120 milliwatts. Of course, that's the efficiency of the transformer, so it's going to be a little more than that. But we consider transformers to be perfect. Transformers do not change power. They change voltage. Now, of course, if the voltage changes in the source, the current in the load is going to change, right? You understand that? So what sets the power is the power of the load. Transformers do not change power. But over here, it will be at a lower current, right? You understand? So what would be my current over here? So the current in my transformer is going to be equal to P over V. So what power are we paying for on that transformer? Transformers don't change power. They change voltage, which in effect changes current, right? You understand that? So what would be the power? I'm sorry, the current. What? And this is the problem we get. People's building power supplies, and they know their current needs 10.6 milliamps, and they fuse the dang transformer at 10.6 milliamps, and they burn everything up. Transformers do not change power. It is a power supply, right? So over here, I'm getting 112 milliwatts at 10.6 volts, right, which requires 10.6 milliamps. And now I'm set, so I would take these through the transformers. You can't take voltage back to figure the current because power varies with the square, right? You understand that? So over here it's taking 933 microamps of work in my... Now I step that up to 1,000 volts. Now we got almost no current, right? Oh, yeah, that's even better.
I'm just handing my zeros.
Now, so what size fuse should we use in the primary?
I thought it was 933. That's what
I don't know. I'm just giving out answers. Obama got 933. So what is it, guys? So Bavana got 933.3. I don't know. I can put it in my calculator. Okay. So what size fuse will we put in the primary? Not 933 because that leaves no safety. Primary fuses, according to NEC, is 300%. And then you round this down to the standard. If it don't fall on a standard value, you round it down to the next standard value. And why they're doing it is they're compensating for the inrush. These are inductors. Inductors, you have to charge them up. And later on, we're going to put a capacitor on here, and we pretty much well got to charge a capacitor. So we got to compensate for that inrush current. And this is probably going to be an MDL fuse, not an ACG. Y'all know the difference between an MCL, an MDL, and the ACG. Does anybody know that most people go out and buy ACGs? In power supplies, we usually use MDLs. What would y'all think the difference would be? Well, one of them is a time delayed fuse. An MDL is a time delay. So what it does is it don't blow instantly. Y'all understand that? An ACG is what we call a fast blow fuse. So as soon as you exceed the range of a fast blow fuse, so if y'all got questions about this, y'all need to be asking me. I'm the one that grades the test. Especially while I'm up here talking. So Larry, what's the difference between an ACG and an MDL? Geez. Joe, what's the difference between an ACG and the MDL? Okay, so I just got through explaining that to y'all, but what was y'all doing? Talking to each other. Okay, people, what's the difference between an MDL and an ACG? Which one's fast flow? ACG. We don't use these, very seldom use these in power supplies. Okay. An MDL is a time delay fuse. So what it does, most people call them slow blow fuses. So they'll handle an overcurrent over time, but it won't be long enough to burn up stuff, and the problem with power supplies is we're charging stuff up, or we're putting that shock on there. Y'all probably noticed most of the time a light bulb blows. If you got incandescent bulbs, most of the time they blow when you turn them on. And because that's that in-run current getting the resistance of the bulb built up. So it takes a little while to get that bulb resistance built up. So if you go in and take an ohm meter and put it across a light bulb, that's not its resistance. It's going to always be lower than what that raised. So it takes an incandescent bulb, it takes a little while for that to build up.
How did you get the pulse frequency?
The pulse frequency depends on what's going on with the AC. So I think I said all the input frequencies are 60 hertz. Isn't that specified somewhere on there?
You just got on the first one.
Now what we do is whatever we come in with, okay, and then we figure out what we get out. So on here, this is a negative supply, so this is what we get out, and those are supposed to line up, guys. So what we do is we've got one cycle out equals one cycle in. So if you got 60 cycle in, then you're going to get 60 cycle out. Now on full wave, we got this. That's one cycle in, but on full wave, we get that out. Y'all understand that? So if it's 60 cycle in, we get 120 cycles out of a full wave. Because a cycle is one repetition of a repetitive waveform. So here, this would be one repetition coming in, but over here, that would be two repetitions coming out. So the pulse frequency would be twice. On full waves, the pulse frequency is twice the input frequency. On half wave, they're the same.
What would happen if you were in a halfway drive?
Well, DC don't care about frequency. DC looks at this. So what you would get is you would get twice the voltage. Or not twice, basically twice the voltage. Now, so you got a device designed to run on 5 volts, and now all of a sudden you pop 10 volts on it. The power varies with the squares, so that means the motor's going to try to develop 4 times the horsepower, and it's probably not going to do pretty well. A DC motor would probably sling itself apart if we didn't protect it. Either that or burn up, but odds are it wouldn't. What a DC motor does, it's really, really interesting, is that the way it works is that, y'all seen DC motors before? I could pass one around, but what we got is we got a wound coil. And we put current into that thing, and it generates a magnetic field. And then the brushes are all set by 90 degrees, which will cause it to spin. And then what we have is we have a unit called a commutator that constantly switches. Well, as soon as the armature starts spinning, it generates a voltage back into it. And the motor tries to run at a speed where the motor generated back into it equals to the applied voltage, but it'll never be that. So that's why when you raise the voltage, the motor has to speed up to counter effect the applied voltage. So what happens is that's the way the motor works. So if you apply twice the motor speed, twice the voltage, the motor will try to run twice the speed. Now what's going to happen? Well, odds are that motor is designed to run at a certain RPM. And you got that armature spinning, it's got all those wires in there, and what happens, you know, anybody ever been on one of those mechanical merry-go-rounds and you're on the outside of that sucker and they start spinning the thing real fast? And, you know, when you're running real slow, no big problem. You get up to speed, what does it want to do? It want to sling you out of there. That's the same thing through with the windings. So if one of those windings separates and gets out and hits the stationary part, you got a big problem. So yeah, we don't want to over voltage a DC motor because it'll overspeed it. So all that, did I answer your question? But if you put a half-wave rectifier on a full, if you lose one of your diodes, then your DC motor is going to run half the speed. What you're expecting out of it. So that's one good indication. So the output voltage is real low. So that's one thing you would look at if you measure in the meter and you're expecting a minus, 10.6 and you're getting a minus 5 something, then odds are what's happened? Yeah, one of your diodes is gone. The next one is what we call a full wave bridge rectifier. So that is called a half wave rectifier, right? You understand. Then we have a full wave center tap rectifier circuit. And then the last one we have is a full wave center tap. What do you mean? Full wave bridge rectifier. By the way, what's neat about these? Let's see if I got one up here. These guys are so common, and I think I told you you can buy the full wave center tap diodes as an integrated circuit, and these guys right here are most often actually integrated circuits. I'll find one when we go on break and show y'all that. So we got high current ones. I'll show y'all some nice high current bridges. And of course show y'all how to check those with an ohm meter, because you're going to run into those in DC power supplies. We'll pop the trainer up, we'll take the trainer up and actually start looking at its power supplies. Okay, so what's the name of this? This is a full wave bridge rectifier. Yeah, and understand, this does not have to be drawn like this. This is just the way they gave it a name. I prefer to come in. So this is what I'm doing to determine what the polarity is I'm looking at these set of diodes right there. I'm not even concerned with the other. I'm looking at that set right there. And notice the anodes are pointing toward the what? toward the source. So that means this is a plus supply. That's all we have to do. Just look at the ones that's what we call the hot side and not the common side. That makes sense? And of course I told you, so this is a positive supply. Well, a lot of times you'll see it drawn like this, which is the way I prefer to draw it. Because all I got to do is put two lines and put four diodes all pointing in the same direction. And then this right here would be my plus DC. This right here would be my minus DC. And then I'm going to bring my AC right in here to the center. That's the same circuit. So notice this sees an anode cathode, this AC sees an anode cathode, this AC sees an anode cathode, the plus, and this is the way you'll see it done a lot. A lot easier to draw, right? So, what's the first thing we need to do? You can calculate the peak voltage and then divide it by the ratio, or you can go ahead and divide it by the ratio and convert the peak voltage. So we'll just do it one of those ways. So let's do that first. So we'd say V out would be equal to 120 divided by 12. What's that going to be?
10.
Okay, 10. Then I can take that and calculate what we call V peak out. No, I'm sorry, V peak secondary. That's going to be 10 volts divided by 0.707, which is 14.1.
14.14.
We round to 1 decimal point in this class, right? Okay, what do I do next? We'll calculate V peak out. V peak out. Let me catch up with y'all guys. Would be equal to 14.1 minus 1.4. So Jackson, you see this, right? Yeah. Okay, what do we got?
4.7.
VP, volts P. Then we calculate our DC. So our DC would be equal to 2 times 12.7 divided by 3.14. What we got? What? Pick up. 8.1. Are we okay? Then I calculate my current. So I of the load would be equal to 8.1 divided by 3.3 K. What does that give us? 2.4 milliamps. By the way, if you don't agree with anything, don't take for granted, that whoever calls it out is right. It doesn't hurt to be wrong here, right? Then we need to calculate P of the load. Everybody okay with that? Would equal to 8.1 times 2.4 milli. What does it give me? What's that? Speak up. Okay.
19
Nope, so there you blew it.
milliwatts.
There you go. 19 milliwatts. Are we okay so far?
Sure.
Okay, then I calculate current in the primary. So I in the primary would be equal to 19 milli divided by 120. What's that? I'm not doing these, guys.
off 2 microamps.
Yeah, probably what I did,
Use 2 digits.
well, what I did is I used my calculator. So a lot of times what I'll do is I'll keep the answer in my calculator and don't drop the digits. So yeah.
Okay. Maybe I got 110. I think that's what it is. I got 158.
Yeah, that's what I got too, 158, but it's, well, it depends on how you round. So 158 is fine. That's only 4 microamps. 4 microamps.
Do you think all of us work this code on our own?
You should.
Same thing?
Not exactly the same answer because all it depends on how you round. So the worksheet probably has 158 micro amps on there. Now, I'm the one that came up with that, and I guarantee you what I did is I just used what the calculator gave me. And then I rounded in my head.
You rather have
No, I didn't round it. I rounded in my head. I didn't do it in the calculator. I write those down. And of course, if you keep all those numbers and round in your head and don't use rounded values, then you would probably come up and get 158. But what you got to understand, 158 and 162, the difference is 4 microamps.
And in the reality, if you check it,
It's not going to measure these anyway. It's not going to measure these anyway. Because what we're doing is we're using 120 volts on the primary. What's the odds of having 120 volts on a primary? So I could take this power supply at my house and I would have a different voltage. I could take this power supply here, I would have a different primary voltage. But everything is going to be so close, it's not going to make that much difference, right? So y'all understand what we're saying? Turns ratio on the transformer is usually pretty good, but also a transformer has a little bit of DC resistance. All right, and so what happens is that a transformer is not 100% efficient. If a transformer was 100% efficient, it would not get hot. Y'all understand that? But it's got some opposition in there, and anytime you push current through opposition, you get watts. So this is why transformers get hot. Now transformers are on the line of power transformers are on the line of over 95% efficient. So that's why we say power in equals power out. But in real life, power in don't equal power out. But to actually calculate that, you would have to know the exact efficiency of the transformer.
what works?
And then what size fuse I would use, I would multiply that times 300. I'm sorry, I multiply it by 3, which would be 300%. And then I would round it down to the next standard value. Now, we got another one which they allow you to round up. It depends if you fuse both sides. If you fuse both sides, the primary and the secondary side, then what you do is 125%, and you can round down to the next standard value. But that's fusing both sides. So a fuse in the secondary primary protects the transformer, but not necessarily the load, right? You understand? A fuse in the secondary protects the load, but not the transformer. So the best thing to do is to fuse both sides. That gives you the most protection. But what you'll find out is most often they fuse the primary. Are we okay? Okay, guys, I'll take a break. Let me go in here and sign my. Yeah, I'll give y'all the chart. Yeah, I'll give y'all the chart. You can look it up. You can look up what you can do is you look up transformer fusing, and they'll bring up the NEC codes, and they'll give you all the fusing capabilities of that. So instead of trying to remember that, what you need to do is just Google it. And you'll find all types of charts that gives you what you need to do on those transformers. Okay, guys, any more questions on the worksheet? Yes or no? Because there's definitely going to be 3 of these on the test. That comes up when? Tuesday, right? I'm sorry, Monday. So I got
Now, get them.
Oh, Wednesday.
Oh, never mind, I'm here on Tuesday.
Yeah, Monday. So if y'all got any questions on this, you need to ask them now.
Are you gonna ask for all the values?
I don't know. I can't. No, we don't. We're not going to do fuse sizes right now. But you need to understand, and this is very important that people get messed up on, is the power in the secondary and the power in the primary are the same. Now the current's different, and this is the advantage. One big advantage of AC. Now AC has some problems, and we probably won't get any time to talk about this, but transformers are basically inductors. And then anytime we get a conductor that's got AC in it close to ground or close to another conductor, we create something we call capacitors. Now notice each one of them has F in it, which means it's dependent on frequency, right? Understand that? So if I get into a DC circuit, I don't have to worry about X of L, I don't have to worry about X of C. So with the so used to all power transmission was AC. But there's a new thing in town, they call it extremely high voltage DC. So with the rectifier circuits that we got right now, what they can do is they can convert it to DC for transmission. And now all we got to do is worry about the R of the wire. Right, you understand? But we're doing extremely high DC values. And then on the other side, we re-invert it and turn it back into into AC. And they're starting to use that, especially over in Europe, for extremely long distances. Like they got a cable going under the canal, under between Britain and France over there somewhere, and they got a power cable running through there. Well, it's DC. For one thing, they don't have to worry about putting it in salt water. That changes the dielectric of the cable. So actually, if you can get DC up extremely high, it's more efficient to transmit DC because you don't have to worry about X of L or X of C, which is real nice. But we're talking about extremely high DC because you want to get that current down to almost nothing, right? You understand, to get that power over. Here in the United States, as far as I know, we're not transmitting high voltage DC anywhere. All ours is AC. All our I don't know. I'd have to go back and research it. That's a good question. You can go and probably research high voltage DC transmission and see. Actually, I'll probably show you the places they're actually using that. But they are using it because now they don't have to worry about X of L. They don't have to worry about X of C. Used to, though, we couldn't step that DC up that high. We had no way of getting extremely high voltage DC. But now with the solid state devices we have, we can efficiently convert it into DC, and then efficiently with inverters and convert it back over to AC on the other side. But DC does not run to anybody's house, and DC does not run to anybody's industry. We're talking strictly transmission. And usually underwater, under the ocean too. All right, so we okay, guys?